right. While we're getting the technical difficulties out of the way. Welcome.
Okay, cool.
Welcome.
There we go.
This is. Oh, there we are. The week before the last week of classes. I'm so glad that you're all here. We have 4 talks for you today, although I have not seen the 4th presenter yet, so I'm sure it's going to be here. We're going to start with these 2 gentlemen that wrote an app for a Rumba as part of the partial really requirements for our CS 470, the capstone course. Please go ahead.
Okay, so I'm Nick.
I'm Brett.
And this is our project called the Rumba Wizard.
So we had this idea that maybe the kids could play with their RC car and vacuum at the same time, sort of was the inspiration for this. So we thought of the Roomba, and we're like, wouldn't it be cool if you could control it via an iPhone app? And turns out there's actually a way to interface with this vacuum through a serial port. And so we got this little module that turns it into its own Wi-Fi network. The nicer Roombas have it built in, so you can connect via Wi-Fi and send opcodes over TCP to the Roomba, telling it to do anything, or a lot of stuff. Like you could tell it to play songs, or drive around, or turn on its vacuums and control that. Also, you can get like the current charge, the temperature, and so there's a lot of opportunities for messing around with this. So what we've built is a Swift wrapper around just like your box standard C socket library that sends these opcodes through TCP. So just demonstrate that.
So this is like our interface right here. We have a little tooltip menu that kind of tells you what all the buttons do. It's a little off-centered right now. But basically, this is to connect to the Roomba. So my device is obviously not connected. Only one device can be connected at a time. So he's connected right now. This is spot clean, so it will clean like in place. Or this is actually just cleaning, and this is spot cleaning, so it'll clean a certain place. These are the 2 wheel motors. So this will control the left wheel, which will turn the arrow direction that it's going. So if only the left wheel is moving, it'll mean it's going to the right. I don't have 2 mouses, so I can't go like forward and backwards. And then this goes left. We also have the motor speeds for each of the brushes, vacuum and main brushes. When it's connected, it'll tell you the charge percentage and temperature, but his device is connected right now. So basically they just rotate like this being full, and then this being like halfway. And we ran some blockers where too many commands were being sent at once in nanoseconds, so it crashed the Roomba, but based off sleep timers and some app delegate things, we were able to send a limited amount of commands so it wouldn't crash every time.
Yeah, we also have you'll notice there's a charge indicator and a temperature indicator. In addition to sending commands directly to the Roomba, we also have a background thread that's listening for these sensor packets that the Roomba sends back to the app. So there's a 2-way communication going on, and so you can see like the charge, going down as if you turn the vacuums on full blast and start driving around like ferociously at full speed, which is also possible. The Roomba usually goes pretty slow, but you can actually get it to go pretty fast here. Let's see here. And because you can control each wheel with such precision, you can actually get it to turn at any arc you want, really. So you can vacuum in a straight line, which the Roomba doesn't do on its own. Kind of just wanders about the room. And so it gives you a lot more precise control over what you're doing. And if you want to go back into auto mode, you also have that option.
Which is right here.
Yeah,
auto mode.
Usually the Roomba has like commands to dock or to clean in a specific spot, or to just clean all over the room. And then if you tap the button again, it gives you full control again.
And then also, just besides accessing the basic Roomba commands, did you just overload?
Yeah.
Oh, okay. You want to reconnect, or did it already do it?
Yeah, so we haven't tuned it perfectly.
Yeah. So besides just accessing the basic functionality of the Roomba, we kind of just branched off and we found out that you can play sounds, a whole frequency, all 81 keys through the Roomba. So we made like a music pad, so you can play music through the Roomba and send it different notes. And we wanted to be able to play chords and stuff, but it only allowed single notes to be passed through at once. And if we get it reconnected, we can show you.
Hopefully. Just a second. Yeah, there's still a few bugs that need to be worked out, but
Sometimes it just gets overloaded with commands and then it just crashes, but
I have a question.
Mm-hmm.
My room got stuck under my bed. What do you do if it gets stuck?
we actually had a problem with our Roomba. It was on auto clean and it went underneath the couch and it ripped off the little wireless chip on top of the serial port and it broke it. Yeah.
cool. I guess we won't be
Yes.
playing
I mean,
these songs.
yeah, it's not reconnecting, but we have a little music controller that plays music. It might go right now. Let's see.
And a look.
Okay. Well, that's our project.
Questions?
Yeah.
I just wanted to congratulate you for creating the most ingenious way to get kids to clean.
Thanks. Okay. Well, thank you. Oh.
Oh, yes.
I'd like to suggest that you market it as a cat toy. There might be
The cats are intrigued by it, but they're definitely too scared to go near it.
Yeah.
Margaret Purser also made the same suggestion. We just saw this first time. Here's Matt.
Yes.
So, is the API, did they release like documentation for the API, or did you have to figure this out?
So there was no API, but they did have documentation for the opcodes you could send to it. So we built our own Swift API around that documentation. So,
Okay.
Questions? Thank you so much. So Adrian Smith worked with Dr. Gill. Adrian.
So I'm going to be presenting on computational classification techniques for neuroimaging. So understanding the human brain has been a central theme throughout all of human history. By increasing our understanding of the human brain, we improve our ability to treat and detect a variety of diseases. And we also improve our understanding of the brain's weaknesses and strengths, which is really important when we're dealing with long-term planning and decision-making, because the brain is our primary tool that we interact with the world through, and we need to understand that tool. Functional magnetic resonance imaging, or Fmri, allows us to measure localized brain activity. This is largely done through looking at blood oxygen levels in regions of the brain, so it allows us to see where the metabolism is most active in certain regions of the brain. This technique produces rich data about how the brain is working, but it also has a lot of noise in it. So one major advantage of working on this type of data is it's widely available online on places like openfmri.org. We worked with a data set that had 1,452 total different brain scans. So each of these brain scans is about 60 by 60 by 42 pixels. So this is a huge amount of data we're starting with to begin with. And so these categories refer to the image a subject was observing. So we might have one scan, one of those 60 by 60 three-dimensional scans with the label cat. So the person in the fMRI machine is looking at a display, and that display would have a picture of a cat on it. And then we would take another scan with that same image, and then we'd go into a rest state where they're just looking at a blank screen, and then continue doing new stimuli. But the question becomes, if we get a scan that we don't know the label for, we don't have a person looking at the image, and we want to just be able to tell, just from that person's brain scan, what are they looking at? Well, that was our total goal, to be able to, given the fMRI scan of a subject, predict which image they are observing. Now, this kind of test is a really, really important sort of base case for being able to tell what's happening inside the brain, because we know some regions that are involved, we have a really clear stimuli, and we have a really defined way of connecting our brain scan and the stimuli. But that meant differentiating the scans based on the image the subject was observing. And on the right are some of the stimuli we're looking at. So top left would be labeled bottle, face, and then those would both be labeled cat. So when we say they're looking at a cat, we use different images to make sure our results generalize. So we looked at machine learning to start working at understanding this data. So machine learning, as many of you probably already know, it's an information processing technique, and it's largely used in business and clinical settings when dealing with large data sets like ours. So we're focusing on designing algorithms that categorize objects, in our case, because we're dealing with object recognition. So we had to find some defining characteristics and a label for that image, which we have the label from the data set, so we had to decide on the feature. So this is just a brief overview of our pipeline for the classifier. We have our training feature, our training label. We put it into a classifier, and we generate a model that connects our feature for the brain scan and a label for that brain scan. So the feature would be something that describes the scan, some important characteristics, and the label would be something like cat or rest. So to look at what features we wanted to use, we started with just looking at our preprocessed values. That's a 576 long vector of all of the different locations in the brain. And then we looked at a couple ways to transform that data. So we looked at PCA, which is a dimensionality reduction technique. So we were able to take this large 576 vector and shrink it down almost by half, but keep a lot of 99% of the variance. So we're keeping a lot of the important data, trying to get rid of data that's redundant from our data set. And we also looked at things like the 50 highest values or a histogram of values. So we then split our data evenly and randomly into our training and test sets. So that is, we're using a lot of our data for testing, which hurts accuracy, but also means our results are a lot more useful in a clinical setting because you may not be able to do all of this. You may not have labels for the majority of the data, so you want to make sure you can work from a limited training set. So we primarily focused on using the k-nearest neighbors and support vector machine classifiers in our case. K-nearest neighbors is faster, but it also doesn't tend to deal with high dimensionality data as well. So we worked on repeating our tests so that because we're randomizing, we want to make sure that our results were real. So this is the general outline of our whole design. It's probably the most important image. So we have our training feature. That would be the PCA reduced volume or the 576 values. The label would be cat or rest. We put those into our classifier, SVM or KNN, and we get a trained classifier. So that's the thing that models the relationship between the brain scan and the label. So with that model, we can put in a feature, PCA or the full vector, and it will output a label. It'll predict a label for that feature. So if we put in some feature and it says cat, we can compare that to the label that we already have and see is it correct. And so we do that for all of our testing data, and we can get a final accuracy. So in all of our testings, we found that using PCA, SVM performed better than KNN fairly significantly. We got, as you see, our accuracy went from 75.6% to 93.9% just by switching to SVM. And we think that's largely because of how complex our input data is. It's a 576 vector, or at least at the smallest we were getting good accuracy was about 270, around there. So we're dealing with a large data set, and SVM tends to deal better with that. One of our main ways we display our results is through these confusion matrices. If you haven't seen it before, the idea is that you have the predicted label and a true label. So the diagonal is when it's guessing correctly. So we can see, the useful thing about them is that we see these patterns in incorrect guesses. So here it's guessing face incorrectly a lot. And so those can give us an idea of where to look to improve our accuracy. So yeah, overall, we were able to achieve a 92% accuracy in guessing which image someone's looking at, using only half of our data as training data. So our classification methods are effective and repeatable, and one of the most useful parts of what we've done is develop this pipeline, because we can really quickly try this on different kinds of stimuli. So let's say we wanted to start looking at classifying diseases, so classifying brain scans based on the presence of certain neurological diseases. That's something that we could easily apply this, or fairly simply apply this pipeline to, and hopefully get similar results to what we've done here. And we've also gained a variety of insights about the nature of the data we're working with. So we saw several labels which were repeatedly misclassified. Over here, you can see shoes classified, so that's kind of a big question on where that's coming from. So we want to look towards multiple subjects, because we focused on a single subject here. But I think we have a lot of background that we can use to advance into that. We have some previous work we've done with lung scans that'll help there. That's
Questions?
Okay.
Did you ever give it an unknown to see what it would do with the unknown?
That's the testing step.
Well, but the test step is you have a label, so you know what it is. That's just training the model. But after you train the model, do you ever give it an unknown to see what it?
Well, the testing with the training step, we give it the label and the feature, right?
Yeah.
But the testing step, the classifier is not given the label.
So I guess my question more generally is, did you ever give it data that had never been in the training set and wasn't part of the model to see what it would do, how it would classify that data?
Yeah, that was all of the testing. All of the testing was not used to train the model.
Okay.
Yeah, so half of our data.
Well, I think where Mark is coming from is like, if you trained it on pictures of dogs and cats and owls and that sort of thing, what if you gave it a tiger? Like, how would that be classified?
So the classifier trains on the labels we gave it. So if we gave it an image, a brain scan with a label that wasn't in the class, it wouldn't guess tiger if it was. It would never guess tiger. It would be interesting to see the result. My prediction with it was that its guess would be pretty close to random.
So you're getting two unfair questioners because we both worked on machine learning projects, just so you know.
Yeah?
So where did you come up with your feature vector? Is that?
So we actually tested, you mean deciding, how did we decide, or how did we decide which ones we looked at in general? Well,
like your features, have they been applied to other sorts of brain activity?
Yeah, so we started looking at I looked around for some other studies, and we focused on histogram was one that we thought could be useful, or the highest values, because it seemed like, okay, you have this idea of regions of the most activity might be where a lot of the important information is coming from, and we encoded location with that. But testing for accuracy against all of these different features, nothing compared. I think I might have it in here. Yeah. So if we did the top 400 values, we only got a 30% accuracy. So we tried doing top values, histogram, got around 30%. Most of the other features were getting about 30% accuracy.
Well, could you use these same features to tell the difference between a person who's trying to solve Sudoku and someone who's writing a story? Yeah.
So that's the main, I would say the main advantage of this study is that the pipeline is pretty applicable. So if we have the data set for someone who, if we could take the scans and we have the labels, we can train this model and probably get since that's binary, probably better accuracy. Cool. Significantly.
Are you aware of any research or connections between finding these patterns and detecting or diagnosing brain problems, brain anomalies?
So because it's fMRI data, the kind of anomalies we'd be detecting are anomalies in mental patterns. So we wouldn't. I don't know how helpful it would be in detecting things like brain cancer, but if we were looking at something like Alzheimer's, I think in this study we focused on the ventral temporal cortex because it's involved with object recognition, but that's just via masking. So if we wanted to look at something like Alzheimer's, we could focus on parts of the brain that are important to memory and see if we can find patterns there, how strong those patterns are. And it also allows us the whole idea of localization of function. When we're doing these tests, it's also in a way testing those theories, because if you focus on, like we did in this study, if you focus on the ventral temporal cortex and you can predict with a high rate, that means that the ventral temporal cortex is important in object recognition. So
one of the interesting things about the brain is it's an associative memory, not an addressable memory, which is very different. We learn about addressable memories in computer science. Brains aren't anything like computers, in my opinion.
Yeah, but I mean, you still have areas of the brain that are more involved with at least short-term memory acquiring. So I would expect you to be able to get some classification accuracy for something like Alzheimer's, looking at those regions in the brain.
Please talk to Adrian after this session. I know that this is a very interesting topic and lots of questions. Thank you so much, Adrian.
Thank you.
Our next presenter is Mark Ayala, who worked with Dr. Rivoire.
Wow, how do you follow something like that? Well, we looked into the brain, we gave it a picture, and it figured it out, our software. Wow. So before I do that, okay, so how many people in the room have taken 351, computer architecture? All right, you're going to hate me in a few minutes. How many people are going to take 351? Okay, well, maybe a little less hate in a few minutes. I was a student in 351, and in 351 you come up against the processor. So here's this little black box. We've been using it all along. We throw something in, and it gives us something out, and it's great. You don't have to worry about it. It just happens, right? Well, you get into 351, and you have to learn about the data path and the control path and what happens when you take 32 bits of zeros and ones, feed it through the data path, and what are all those values on all those lines, and what ends up coming out the other side? You have to figure that out now. So in order to help students learn what's going on in the data path, how to take those 32 zeros and ones, and come with an answer in the other end, and all the intervening bits, all the intervening values that are on both the data path and the control path. I followed on to a tool that maybe we'll display. Yep, okay, there we go. So there were a couple of guys who built this tool, and I'm going to get their names wrong, Yadel and Wardley?
Eric Woolley and Ortel Yadel.
Thank you. And they built this fantastic tool to allow you to put in a MIPS program, run it. MIPS is another assembly language program. You learned in 242 assembly, right? So this is a different type of assembly, an ISA MIPS. So you can run your program and say, okay, great, it ran. I got a program that runs. When I get to the data path part, and I have this first add instruction, which is equivalent to saying, I'm going to add 0, whatever in T1, and put the result in S0. Those are all registers, right? Those really wickedly fast little places in memory that allow you to store things and work with them inside the processor. What really happened? How did I get my S0 value of 319? Well, let's look at it and see what happens. So here is the instruction at the top. And here it is in binary. Here's those 32 zeros and ones. And all the instructions, as you'll find out, those of you that are going to take it have a format. So everything starts with the program counter. So we grab a value, and the program counter has a value, right? But maybe in binary, it's just not making sense. So maybe it makes more sense in decimal. So I started with 32768, or maybe in hex. So we know what the program counter is. We've got to go get an instruction, right? So instruction, decode. Well, we've got our instruction, and now we put it on the control lines. And so what you're seeing here is, in this class, in 351, you're going to fill these type of diagrams out a lot in order to understand how the instructions in the MIPS ISA propagate through the single cycle processor, right? So this thing has helped you understand it and actually see it. So for this instruction, there we go through the execution, memory, and then what gets written back to S0 is that value in decimal 319. Finally gets written back. So the idea is that you can look at individual pieces. I really didn't understand what was going on. Well, that's everything. I didn't really understand what was going on in memory. Well, there isn't a whole lot more going on in the memory phase, except We're kind of moving around the on-chip memory and coming back with our new PC. Okay, well, what actually happened in the execution phase? So you can look at it individually, you can look at it overall, you can reset it, you can see it all. You can change between, binary, hex. The idea was to validate your handheld process as you start to do this, of taking those 32 bits, putting them on the control and the data paths, and did I get that right? I can go check. Or what does a branch equal look like really? Adds are nice, but what does a branch equal look like when I start to move through instruction fetch, instruction decode, execution, mem, write back? And you'll see that some of the pieces are grayed out because they're not relevant to the instruction. And you'll see that some of the values are grayed out because they're not relevant to the instruction. And that, in the process of doing this, I came from database, which was the last 2 weeks an introduction to web. I don't know if you people have had that class, but that was my first introduction to web. So web development, and then Twitter Bootstrap and D3JS, and using a development system known as WebStorm. So if you take on your senior project and you're going to learn 3 or 4 or 5 different technologies, give yourself a little time. It's kind of a bit of a steep curve for a challenge. And that's it. And it's available at this address. cs.sonoma.edu/me, Emayala, WeMIPS2. Anybody can get to it.
Questions?
Yeah.
This is for Dr. Reward. Are you going to have this available to future students?
Yeah, so I already host the base WeMIPS that Ortal and Eric made, and I'm going to host this as well.
Cool.
Other questions? Thank you, Mark.
Yeah.
So this concludes our speaker series, and our next event is to give awards to the club officers, and Dr. Reward is going to do that. While Dr. Reward is coming here, I just want to really sincerely thank those who are involved with our clubs, both clubs, the CS Club and WICS.
All right, so first the CS Club. So the CS Club president this year was Ben Levinsky. Is he here? Oh, okay. Vice President Jeff Brewer-Keating. Secretary Connor Doherty. I'm gonna get somebody. Tyler Holland, I saw you. You're CS Club treasurer. Get up here. And Jessica DiVincenzi was the CS Club event coordinator this year. Do we want the officer picture?
-2.
Yeah. All right, so all right, so in addition to the Computer Science Club, we have the Women in Computer Science Club supporting our female majors. So the president of WICS this year was Kelly Morales. Let's do that. The treasurer was Dee Dee Powell. The secretary was Melanie Nurnberg. And the event coordinator of everything this year was Jessica DiVincenzi.
speaking of the clubs and the CS club and the absence of some of the officers, so we are hoping to host next time that we meet in Colloquium. We are hoping that we have some nominations for the officers of the club for next year. CS Club is incredibly important to us and to our incoming freshmen and really everyone in the pipeline. So I really want to encourage you to apply for these positions of president, vice president, treasurer, event coordinator. This is an important thing to us. What I'm hoping you would do is send me nominations. If you are interested in serving in any of these positions, please send me a short email, and next time that we meet here, a week from today, we're going to hold elections. I'll just hand out names, and you would circle whichever person you want to choose, and we're going to then collect them and tally them, okay? By the way, Dr. DeVore is going to meet with the Chancellor White in about 20 minutes.
With Scott Walker.
And Scott Walker, one of her students. Next week we will have 2 speakers, and also we will have one of our alumnus giving a talk about high-tech careers, Eric Levinson. Hopefully you're all going to show up. A few notes about courses for next semester. We, as you know, opened a new section of CS 351. And the majority of people who were on the wait list for the first section, which was about 22 students, they have moved and signed up into the second section. Just know that that section is still open. And if you need to take this course next semester or following semester, please consider enrolling in it if you have, of course, the prerequisites, and also you have the unit to do so. I say that basically because we're offering 2 sections of it next semester, so the semester following it, we're going to offer 1 section of 351 and 2 sections of some other courses. So this is a very good opportunity to take this course. There are seats available. I do know that we have a number of students on the wait list for 415, 450, 454, 460. We also have a large wait list for 390, this course, and for 385, Dr. Gill's topics course. The ones that we might be able to help are those who are on the wait list for 415, 450, 454, and 460. Our hope is, it's not at all guaranteed, that we will open 1 section of these 4 courses. And probably, of course, we'll look at the wait list and see which has a larger wait list. And also, of the people who are on the other wait lists, which of them have not taken that course, who potentially can take that course, okay? So I'll have more information for you next week, a week from today. Thank you so much. I appreciate you coming. I'll see you next